Okay, I'm going to show you how to determine the particular solution of a first-order linear homogeneous system of differential equations. Okay, so this differs from our single variable case, in which case now I have two differential equations, and the first differential equation is independent of the second, but the second relies on the first. Okay, because this x1 is tied to the first equation, then they act together, and the behavior of one will affect the other. Okay, so I'm going to determine the particular solution, we'll plot the particular solution, and then we'll discuss long-term behavior. So this is what I'm given, negative 4x sub 1, and then the second differential equation, the change in x2 over time is going to be x1 minus 5x2. Here's my initial conditions. This capital X really denotes the both equations simultaneously in vector form. Okay. So just to verify and classify, I can only do this analytic solution if I have a first-order linear homogeneous system. So I have first order because the highest derivative is the first derivative. It's linear because I don't have any products, powers, or functions of either dependent variable, which is x1 and x2, and every term in the equation includes at least one dependent variable. Therefore, this is first-order linear and homogeneous. Okay, so the first thing is to write it in matrix form, in which case I want to take this and put it in this form: dx1 dt, dx2 dt, and now I'm going to factor out these values. So I have negative 4, 0, 1, and negative 5. And this is multiplied by x sub 1 and x sub 2. Okay, and the way this works is a matrix multiplication. It's negative 4 times x1 and 0 times x2. And it's 1 times x1 and negative 5 times x2. Okay, so this is the piece that I'm looking at. So in my computer system, I'm going to type the command eigensystem, and I'm going to input this matrix: negative 4, 0, 1, negative 5. And that's going to give me my eigenvalues and eigenvectors. Okay, we denote the eigenvalues as a lambda 1 as a negative 5, and lambda 2 is negative 4. And the eigenvectors, k1, I have 0, 1, and k2 is 1, 1. Okay, and because these eigenvalues are real and distinct, I can use a case 1 general solution. Which looks like this. Where x of t becomes c1 k1 e to the lambda 1 t plus c2 k2 e lambda 2 t plus, and if this continues on and on, I can go out to as many terms as the size of my initial matrix is. This is n, to n terms. So here I have 2 by 2, so I'll have two values, 1 and 2, because I had two eigenvalues. If I have a 3 by 3 matrix, I'll get a third eigenvalue, an eigenvector, and have 3 terms in my general solution. So my general solution will look like this. C1, which is my constant of integration, times K1, which was 0 and 1, e to the negative 5t, plus C2, which is 1, 1, e to the negative 4t. And this is my general solution. Okay. Now what I want to do before I apply my initial condition is I like to rewrite it, and this is just my preference. It's easier for me to see if I rewrite this x of t as these individual components. So I want to see x1 of t. And to get this, I'm going to multiply it through the top of this eigenvector in each term. So it's c1 times 0, which this term will become 0, then c1 times 1, or c2 times 1. So I'll have c2 e to the negative 4t represents the equation x1 of time. x2 of t is going to be c1 times 1 e to the negative 5t plus c2 times 1 e to the negative 4t. Okay, now that I have these in this form, I can easily apply my initial conditions. So the initial conditions up here at time 0, x1 is going to be at 2. So I can say 2 equals c2 e to the negative 4 times 0. So this is at time 0, the first equation equals 2. And I know anything, and I've raised anything to the first 0th power becomes 1. Therefore, c2 equals 2. And for my second equation, I can use this 4. Let's say 4 equals c1 e to the negative 5 times 0 plus c2 e to the negative 4 times 0. Simplifying this, this term goes to 1 as well as this. So I have c1 plus c2, but I already solved for c2 here. So I can just input that value. And then solving for c1 by taking this 2 and put it on the other side of the equation, I will get 2 as well. Okay, so the last step is to write out my particular solution. Just inserting my known constant values now. x1 of t is 2e to the negative 4t, and x2 of t is 2e to the negative 5t plus 2e to the negative 4t. An alternate way to write this particular solution would be back in this original form of x of t, the capital X of t, as a vector, in which case I know c1, 2 times 0, 1, e negative 5t, okay, and these are the same thing. Okay, and then the last thing I want to do is I want to verify. Okay, so a verification process just is a check and balance. Did I do the math correctly? Did I correctly compute my eigenvalues and eigenvectors? And the first thing I need to do is take the derivative of my answer. So I need to find x1 prime of t. And that's the derivative of this term, which I get my e back, negative 4t. Chain rule, this will be negative 4 times 2, or negative 8. x2 prime of t, the first term will be a negative 10 e to the negative 5t minus 8 e to the negative 4t. Okay, so now what I want to do is I want to substitute these values and these values of x1 and x2 and x1 prime and x2 prime into my original differential equation. Okay, so here I'll verify my first equation. Okay, this term represents dx1 dt, and this term represents x1 of t. So x1 of t I have right here, 2e to the negative 4t, and dx d1 dt is this term where I took the derivative. And if I multiply that out, you can see that this will become negative 8, and the left side equals the right side. So yes, x1 of t is a solution. Okay, So let's do the second equation. Second equation, I'll start off with negative 10 e to the negative 5t minus 8 e to the negative 4t. Okay, and my differential equation was x1, which was 2e to the negative 4t minus 5 times x sub 2, which was 2e to the negative 5t plus 2e to the negative 4t. Okay, so if I multiply this out, this becomes negative 10 e to the negative 5t minus 10 e to the negative 4t. And if I carry this term down, okay, now you see these terms, the negative 4t, the 2 and that will combine to make negative 8 e to negative 4t, and I keep negative 10 e to negative 5t. And now you'll see that the left side does equal the right side again. Yes, x sub 2 is a solution. Now let's take a look at the plot. Okay, I use Mathematica, and I started off here with the eigensystem, and this is the matrix where I found my eigenvalues and eigenvectors. These represent the eigenvalues, and the bottom row is the eigenvectors. Okay. So here I'm inputting these, I'm defining these in Mathematica using a solve command, and this gives me my particular solution. Okay, I can verify my particular solution here. So I'm copying, pasting this value and putting it here, and this value and putting it here. And then this is the original system of differential equations where I'm asking the question, does the left equal the right? And it says true, which means it is in fact a solution. Okay, and because I've defined x1 of t and x2 of t, which was my particular solution here and here, I'm calling those functions down here in my plot command. Okay, and you see this is my plot, and the orange line starts at 4, which represents the second function. Okay, so here I have orange as the second color that will represent x of 2, and the purple line starts at 2, and you see that the long-term behavior is they're very quickly approaching 0, okay, in about 1 unit of time. Now, one interesting thing to note is that how the system behaves dependent on the eigenvalues and eigenvectors. So in my case, my eigenvalues were negative. Both of them were negative. So when you take a look at this particular solution here, if I raise e to a negative number, it's going to get extremely small. So if one of these eigenvalues, one or both, become positive, then the system should diverge very quickly. So I can quickly demonstrate that in my computer program by removing one of the negatives. So I'll make that a positive 4. This eigenvalue, instead of a negative 4, it's now a positive 4. This eigenvector stayed the same, and this one changed to 9 and 1. My initial condition remains the same. Okay, and now I have a new particular solution. Okay, and we should see this diverge quickly. And you see here, because we had that positive eigenvalue, then our system is diverging.